All right, so today we're going to tackle one of the most fundamental and, let's be honest, one of the coolest rules in the entire universe. Seriously, this is the rule that explains why time only seems to move in one direction. It governs literally everything, from why your morning coffee gets cold to, well, the ultimate fate of the stars. So let's just start with something you see every single day, right? You pour a hot cup of coffee, it always cools down. You scramble an egg for breakfast, it never unscrambles itself. I mean, can you imagine? So what's going on here? What's the big cosmic rule that dictates this really strict one-way flow of events? Why does the universe feel like a one-way street? All right, Section 1, the first law's big problem. Now, to get to the bottom of this, we've actually got to start with a law that doesn't explain it. In fact, this law has a huge gaping hole in it when it comes to the direction of time, and that's the first law of thermodynamics.
Okay, so the first law is basically the universe's accounting department. It's all about conservation. It tells us that energy can't be created or destroyed. You can change it from one form to another, but the grand total in the universe, that's constant. It's a perfect balance sheet. And it's absolutely true. But, and this is a big but, it's missing a crucial piece of the puzzle.
And this is where we see the first law's big problem in action. See, it has absolutely no opinion on the direction of things. As long as the energy books are balanced, the first law is happy. So, according to this law, a lukewarm cup of tea could totally just suck heat out of the cool air around it and start boiling all by itself. The energy would be conserved. But we know that's absurd. It never, ever happens. That tells you something else has to be in charge here. There's another rule at play.
Section 2, enter entropy, the real boss. So yeah, if the first law is perfectly fine with these impossible things happening, what law isn't? What's the real boss? Well, this brings us to the hero of our story today, the second law of thermodynamics, and this amazing, powerful concept called entropy.
Okay, first things first. A lot of people hear entropy and they immediately think disorder or messiness. And, well, that's not wrong, but it's a little misleading. A much, much better way to think about it is this. Entropy is a measure of how spread out, how dispersed energy is. You see, energy just doesn't like to be all cooped up in one place. It has this fundamental natural tendency to spread out. It wants to be free, so to speak.
And what's so fascinating is where this idea came from. It wasn't some astronomer gazing at the cosmos. Nope. This whole concept was born out of something much more, well, gritty. It was born from the smoke and steam of the Industrial Revolution. Engineers were just trying to build better, more efficient steam engines. They wanted to turn heat into useful work, and in that very practical quest, they accidentally stumbled upon one of the most profound and inescapable truths about how our universe works. This statement right here, the Kelvin-Planck statement, sounds a bit dense, but what it's really saying is super simple. A perfect, 100% efficient engine is impossible. It's a fantasy. You just can't take all the energy from, say, burning coal and turn every last bit of it into useful work, like moving a train. It's just physically not possible. So let's break down what's really happening in any engine. First, you take in some high-quality concentrated heat. Think of burning coal. Then, you use some of that heat to do something useful, like turn a turbine. Great. But here's the kicker, step 3. You inevitably have to dump the rest of that energy as low-quality, spread-out waste heat into the surroundings. You just have to. There's no way around it. And that unavoidable spreading out of energy, that is an increase in entropy. It is a fundamental law of nature. Okay, Section 3, how spontaneity actually works. And this right here, this inescapable spreading out of energy, this is the key to everything. This is what builds into the ultimate rule for why anything in the universe happens all by itself. All right, so to figure out if something is going to happen on its own, what scientists call a spontaneous process, you can't just look at the thing you're interested in. You can't just look at the cup of tea. No, you have to divide the universe into two parts. First, there's the system, that's our cup of tea, and then there's the surroundings, which is, well, literally everything else in the universe. And to know what's going to happen, you have to look at the total change in entropy for the whole shebang. And here it is. This is the big one, the master rule of the universe. For any real-world process to happen all by itself, I don't care if it's a star being born or your tea getting cold, the total entropy of the system plus the surroundings has to go up. It must increase. End of story, period. This right here is the universe's ultimate one-way street sign. This table really lays it all out. If the total change in entropy for the universe is positive, greater than 0, the process is spontaneous. It'll happen. If it's negative, Nope, not going to happen. So let's go back to our tea. Why does it cool down? Well, as the cup itself cools, its own entropy goes down a tiny bit. But the heat that spreads out into the much bigger, cooler room, that increases the entropy of the surroundings by a huge amount. So when you add it all up, the total change for the universe is positive. And that's why it happens. It's just following the rules. Section 4. What is free energy? Okay, so that's all great, but are we really supposed to calculate the entropy change of the entire universe every time we want to know if something will happen? I mean, that's just insane, right? Totally impractical. So, brilliant scientists came up with a clever shortcut, a way to focus only on the system we care about, and it's called Gibbs free energy. Okay, I love this analogy. Think of it like this. For any process to be allowed to happen, it has to pay the universe. What's the payment? It's an entropy tax. The process has to dump enough dispersed energy out into the surroundings to make sure the universe's total entropy goes up. It has to satisfy that demand from the second law. It's a non-negotiable tax. So once that mandatory entropy tax is paid to the universe, the energy that's left over from the process, that's what we call Gibbs free energy. It's free because it's no longer obligated to the universe. It's now available to do actual useful work, like powering your phone's battery or driving a crucial chemical reaction in your body. And this brings us to the key takeaway for Gibbs free energy. When you see that a process has a negative delta G, that's the magic number. It tells you two critical things. One, the entropy tax has been paid in full, so this process will happen on its own. It's spontaneous. And two, there's actually energy left over that can be harnessed to do something useful. A negative delta G is basically the universe giving that process a big green light. So, this leads us to a final, pretty mind-bending thought. We've established that the universe's total entropy is always irreversibly increasing. It can only go up. Energy is constantly spreading out, moving from these nice, useful, concentrated forms to a state of complete dispersal. So where is this all headed? What's the end game? Well, this relentless, one-way march towards maximum entropy has a pretty chilling name: the heat death of the universe. It's this theoretical future where everything, everywhere, reaches the exact same temperature, a perfect equilibrium. If that happens, there's no more heat flow, which means no more energy to do work, no more change. Nothing happens anymore. It would be the final, quiet, and ultimate end of the universe's one-way street.